Let's uncover the picture and focus on Newton's third law. What do you notice in the picture? I see smoke. I notice the smoke is in the sky. What else do you see in the picture? Now I see the ground. I predict the next section will be a rocket. Newton's laws are represented in this picture by a rocket launch. For every action, there's an equal and opposite reaction. So here, the action, the gases are expelled from the rocket, and the rocket is propelled forward, reaction. So again, action, gases are forced downward, reaction, rocket is propelled forward. So the gases that are pushed downward have the same force as the rocket being pushed forward. Watch the video on Newton's third law of motion. For every action, there's an equal and opposite reaction.
Hey, it's Professor Dave. Let's talk about Newton's third law.
He knows a lot about the science stuff. Professor Dave explains.
After learning about Newton's first law of motion regarding inertia, as well as the second law regarding the proportionality of force and acceleration, we are ready to round out the trio and look at Newton's third law of motion. This is most famously stated as follows. For every action, there is an equal and opposite reaction. While this is often quoted out of context for metaphorical purposes, in physics it means something specific and quantitative. It means that if two objects interact, the forces they impart on each other will be equal in magnitude and opposite in direction. Think of a car hitting a brick wall. The car imparts an action force on the wall from its motion, and the wall imparts a reaction force right back on the car, bringing it to a quick stop. These vectors are equal in length and point in opposite directions. What this also means is that there can never be a single isolated force, as any force is an interaction. Forces must always exist in pairs. As you sit in your chair right now, the force of gravity is pulling you down towards the center of the earth. But something called the normal force points straight up with the same magnitude, which is why you remain perfectly still. We will learn more about this force later. The third law can sometimes be confusing because it would seem to imply that no object could ever move, since any force accelerating an object must be paired with another in the opposite direction. For this reason, we must understand that when assessing the motion of an object, we consider only the forces acting upon that object and not the forces that it applies on other objects. When hammering a nail into a piece of wood, the hammer imparts force onto the nail, and the nail imparts force onto the hammer. But the nail is driven into the wood because there is a net force acting upon the nail from the motion of the hammer. Likewise, the hammer has two forces operating upon it, the downward force from your arm and the upward force from the nail. That's why when you strike the nail, the hammer stops moving at roughly the location where the impact occurs. So if we are looking at the nail, we only consider the forces acting on the nail. If looking at the hammer, we only consider the forces acting on the hammer. These are different systems, and this is the context in which the third law is best understood. Let's look at another example. When a rock falls to the ground, the gravitational force from the earth causes the object to accelerate towards the earth, but it is also the case that the earth is accelerating towards the rock. This must be true according to the third law. Of course, we don't notice this in everyday experience because the acceleration of each object is inversely proportional to its mass. The rock is very light, so the rock accelerates quickly. The Earth is very heavy, so Earth's acceleration is completely negligible. This may seem a bit abstract, but it is important to be able to rationalize forces in this way. So there you have it, the law of inertia, F equals ma, and action-reaction. That wraps up our discussion of Newton's laws of motion. So let's check comprehension.
So let's read this. When a bowling ball strikes a bowling pin, which imparts a greater force upon the other? So neither would have a greater force. The forces are equal. So the bowling ball strikes the pin with the same amount of force the pin strikes the ball.